This is a tutorial to visualize the Old Faithful dataset using a couple of packages in Python. Now, the dataset that we're going to be visualizing is stored in a CSV file, or comma delimited file. You can see here some of the entries. This file is structured as having a series of observations of Old Faithful's eruption. These include both the observation number, followed by the duration of the eruption in minutes, and then finally the number of minutes waiting until the next eruption occurs. Now, to visualize these data, we're going to be using a Python script to import the CSV file into Python data structure, and then plotting and performing statistical analysis of the data. We're going to be using two packages in this example. First one that we'll import is the Numpy, or numerical Python package. So I'm going to import Numpy as NP, so this is the shorthand to refer to the Numpy package. The second package I'm going to import is actually one called pyplot, which is in the Matplotlib package, pyplot. This is a plotting package that will allow us to create charts and other visualizations and see this data. I'm also going to give this a shorthand PLT. Alright, so I'm going to save this example and start getting to work. The first thing we want to do from the Python script is to import the Old Faithful data set. And the easiest way to do this from a comma delimited file is to first create a new variable data to store the results, and then from the Numpy package to use a function called gen from txt. This is a function that if you hit Control-I to inspect the object attributes, you can see it has many possible parameters, but the basic set that we're interested in is first to list the file name of the file to read, and then also to include options to specify the delimiter and how many header rows should be skipped. So in this case, I have the faithful.csv saved in the same folder as the Python script. So the file name I want to edit is simply faithful.csv. And to specify these as commas as delimiters, I can add in the optional parameter delimiter equals, and then comma in quotation marks. And finally, to skip that first header row, I'll add in the option to skip underscore header equals 1. Now, this command, which I can run from the script right now, will produce this data object. And we can see in the console by displaying the results of this data variable, it's a two-dimensional array, or an array of arrays, and each of the rows of the text file is represented as a separate row with 3 columns. The first column is not numeric, so it's assigned the special value NaN for not a number. Meanwhile, the other 2 columns produce the eruption duration in minutes and then the waiting time in minutes. So let's get to work to first visualize this data. So I want to plot this data, but the eruption duration and the waiting time on 2 axes of a plot. So the first thing I'm going to do is to create a new figure using the Matplotlib library, using the instruction plt.figure. This will generate a new figure just in case you have an existing figure you're working on before. Now, with this figure, what I want to do is to use the plot functionality in Matplotlib. This function, if you inspect its object properties by pressing Control-I, takes in a number of options as well. The general use of it is shown in this example, where you want to list the X data, then the Y data, and finally any formatting options that you may want to choose. In this case, we want to plot the eruption time as the X data, so that's stored in the first column of the data structure. And to reference the first column, we can use this notation of brackets to index elements of the array. But we want to get all of the rows as the first index. That's what this colon symbolizes, to get the data from all of the rows, but only column number 1, which again, using the 0-based index, is actually this middle column in the data structure. And similarly, to get the waiting time for the data, we can type in data square brackets :2. And this data, for example, I want to simply plot with a blue dot. The format for that is a period and the letter B for blue. So if I run the script as it is, we can now see a very basic plot down here in the console. It doesn't have any labels on it yet, but we can add those next. And just to show this indexing notation again, if I look at the whole data structure, I get all the rows with all 3 columns. If I type in to just get all of the rows but only the first column, it'll return a nice array of only those eruption durations. And then the second column will get those waiting times between eruptions. Okay, so I'll run my script again. This is the plot that we're currently working with. It's displayed in the Spyder console, but if you wanted to, for example, copy and paste it into another program, you can simply right-click it, copy image, and then you can paste it, in a separate program. First couple of things we want to do are maybe to label the axes. So the first, using the plotting package, we want to change the X label. We want to change it to the eruption duration in minutes. So this X label is a function that lets you override the label. There we go, we got a nice X-axis label. We can do the same for Y label. Set it to time between eruptions. It's also the waiting time. This is in minutes. All right. And we got our nice Y label as well. One of the things that you may want to do, so this, you can see that the Y data is only showing kind of a portion of the overall range. It starts at 40 minutes and goes up to 100. If we wanted to show the entire range, we could change the plot Y limits, YLIM, and give it a new array or a new list with just a lower bound and upper bound. So maybe we want to display this data from 0 to 100. So that pushes these data further up so we can see the entire range from 0 to 100 minutes. So we can start to see some structure in this data. One of the things that we're going to do is start overlaying some analyses on this plot. So one of the things that will help us later on is actually to give a legend in this plot as well. plt.legend, and if we run this, it doesn't actually display anything yet. The reason is we haven't given these data a label to include in the legend. So if we go back to the plot command, we're plotting column 1, column 2, blue dots, and we're just going to assign these to a label of observations. And with that observations, our legend now appears. You can see that it's obscuring or covering up some of these plots. So one good thing, a good option to include in legends is to change its location. So location is one of its optional attributes. And that location I like to use most often is actually just a string called best. It figures out what's the best location for this legend based on what data is being displayed. Okay, so we have our plot of data. We can see that there's kind of 2 clusters of data, but there appears to be a general positive correlation between eruption duration and time between eruptions. Some of the first steps that we could do to analyze this data are to run some descriptive statistics. So maybe we'd want to know what's the mean eruption duration. So we could, over here in our script, create a new variable for duration mean. And to compute this, we can use a built-in function in Numpy, np.mean, and provide it the data that we want to take the mean of, which again is that first, or column number 1 in the data structure. So if we run the script and take a look at duration underscore mean, see that the mean duration is about 3.5, which looks about right on the plot. So it looks like we have the right function here. We can do the same thing for the waiting time. Wait underscore mean, it's np.mean, data, all of the rows, column number 2. So wait mean. You can see after running the script, the mean wait is somewhere around 70, 71 minutes, which again looks about right from the data. The other two descriptive statistics that we might be interested in are the duration standard deviation. This is another built-in function in Numpy, std. Run it on all of the rows, first column in the data for duration, and also for the waiting time. Find the standard deviation of the data. Right. Looks like I have an error here, invalid syntax. Oop, I put a semicolon instead of a colon, so I'll just fix that right up. So one way of visualizing these descriptive statistics is to overlay them on this plot. And just to show you another option for plotting, there's, in addition to just using the plot command in Matplotlib, you can plot an error bar, which you can kind of see from the tooltip here. You specify the x location, y location, and then the length of the bars that extend from that point. So in this case, we can, for example, create an error bar at the mean duration and the mean weight. And for the error bar length in the x direction, let's have it be the standard deviation of the duration. And the length of the error bars in the y direction, let's make it the waiting time, standard deviation. So we can see after running our script, the error bars now extend from the sample mean in both variables and stretch out to be one standard deviation width. One thing I'm going to do though is just to make this a slightly different color. So rather than the default, which is this blue color, I'm going to change it to create an X mark at the center point, at the mean, and then use the red color, or R, the red pen, to draw those error bars. One thing for the error bar, you can see I got an error here from running this script. You can't just specify the format at the end of the line. The reason is that there's an option that doesn't have a keyword, like this X error or Y error, can't follow one with a keyword. The other thing with the error bar, it actually requires you to have a keyword for formatting. So in this case, the keyword is FMT. So FMT stands for format. It's the format for the error bar. Here we can see that, again, after running it correctly, we get a nice little X at the means, and then these error bars extend out one standard deviation. Last thing I want to add, I'm just going to extend these down to the next line. I'm going to give this a label as well. Label it the descriptive statistics, so that if I redo the legend, in the best location, now I'll get both the labels for the observations and the descriptive statistics. All right, the last thing that we can do is to try to fit a regression line to this data. We can see that there seems to be a positive correlation between these two variables, but maybe we can investigate that a little bit more in a regression. So Numpy has built in a linear regression function. It's called a Polyfit. It's actually a polynomial regression, but we can also do simple linear regression as well. Looking at some of the required arguments in the object instructor, we can see the three main ones are the x data, x coordinates of the data, y coordinates of data, and the degree of the fit. So in this case, our x data is again column 1 of data, y data is column 2, and in this case we just want a single order regression, meaning it'll be of the form y equals mx plus b. So just a single order fit. This polynomial function will return a, we go down to the returns section. It returns the coefficients of the polynomials, highest order first, or highest power first. So if we just store these in a temporary variable like coefs, run the script, we can take a look at the coefficients. We can see the first one is 10.72, the second is 33.47. These are the coefficients for x and the constant. So our overall equation seems to be that the time between eruptions is 10 times the eruption duration plus 33 minutes. We can visualize this by plotting another thing on the screen. So we can, we'll first need some samples for eruption durations to print, to plot. So I'm just going to create a variable called plotx that has, and that is just an array of two values, and these are just going to be the lower bound and upper bound of the x coordinates. So we're going to draw this linear regression straight from about 1.5 reaching up to 5.5. So these are the 2 points that we're going to, these are the two boundaries. Now the equation for the y values is computed based on these regression coefficients. So remember the functional form was that first coefficient, which is actually index number 0 in that coefficients array, times the x variable, which in this case is a list of 1.5 and 5.5, and we need to add then the constant, which is coefficients, the first index. So now we have x and y coordinates for some sample data to plot following the regression. We can use the plotting tool again to plot the x and y coordinates. This time I'm going to use a dotted red line, so as a format. So colon means making a, sorry, typo there. Colon means making a dotted line, R for the red pen. And this one I'm going to assign a label to as well, calling it linear regression. And then just finally update the legend. Alright, so we now have our updated plot. There's this line that's been drawn between the x equals 1.5 and x equals 5.5 at the value of these two regressions. We can actually investigate that. What's the plot y coordinates? It's about 49.5 on the low end and then 92.5 on the upper end. Now this works well because it's a linear regression, meaning that we only need to know 2 points. But sometimes you may have a regression line that has curves in it, so if it's a second order regression, for example. So in those cases, rather than just assigning 2 points to the x coordinates, we may actually need a linear range. So Numpy has a nice function called linspace. Linspace returns an evenly spaced numbers over a specified interval. So maybe in this case we could make the interval between 1.5 and 5.5. I'll just rerun this for example. We get the same results again here because it's a linear regression, but if we look at the x coordinates now, we get a whole list of options that are being evaluated. Same for the y coordinates. We get one y coordinate for each of the x coordinates. Last thing we may be interested in is to compute the fit of this regression. So we're interested in the coefficient of determination, or correlation coefficient for this polynomial fit. Numpy doesn't have a way to get it to return it straight out of this polyfit function, but we can use a separate function to access the correlation coefficients. It's the Numpy coef function. So if we look at the object inspector for this function, we specify the x data, the y data, and then it will return the Pearson product moment correlation coefficients. Let's just try this to see what it looks like. So we want to find the correlation coefficient between the first column of data and the second column of data. Well, column 1 and column 2. And I'm going to store these as the R matrix. So the result of this function, correlation coefficient, is a variable R matrix. If I inspect it in the console, see it's a square matrix, has ones along the diagonal, and the off diagonal is 0.9 in this case. That 0.9 is actually the R value. So the R value is our matrix. You can see they're equal. They're always going to be equal in these types of simple cases. The first row, row 0, column 1, and usually what we're most interested in is the R squared value, which is the R value to the second power. Take a look here. So our value is 0.9, and then the R squared value is 0.81, which looks exactly like 0.9 squared. So what that means is that in this data set, this regression line that traces this straight line explains about 81% of the variance of the data, and the remaining 19% of the variation measures how far these points stray from this regression line. That's the unexplained source of error that's probably due to natural processes or measurement errors in observing this phenomenon.